Hello and welcome to Decision Support Systems for Managers. Today we are into module 2, that is Models in Decision Support System, and lecture 5 of module 2, that is Solution Techniques, Optimization, and in particular integer programming. What have we covered till now in module 2? In module 2 we have covered till now what is a structured problem, what is a semi-structured and what is a unstructured problem, what is a model, classifications of models, purposes of modeling, solution techniques, traditional approaches, desirable features of models in DSS, models and managers, the concept of a decision calculus. These we have covered. We were in specific pointing to solution techniques, that is optimization, heuristics and simulation. This part we were covering. Okay. Now, just a quick recap, we have covered what is a structured problem, what is a semi-structured problem and what is a non-structured or an unstructured problem, and then what is a model, right. What is a structured problem? Structured problems are very simple, easy to understand, we can put them in certain structure. I gave you the example of a building construction. In a building construction, if it is a concrete construction, what is done? First, the iron rods are tied. The iron rods are tied together in a particular format, and then wood or steel planks are put on all the four sides, and then concrete is put in. Okay. That makes a structure. So, structure follows a particular format. It is easy to do. It has some calculations involved. Okay. And if you do it in the proper manner, it will give you the proper result. So, where and in which cases do we find a structured problem? We gave you the example of a production problem. That is, I have these resources, this is my profit for the product, two products, I have two products are there, these are the profits from the two products and these are the resources available. So, which product I should manufacture and in how much quantity. So, this is a structured problem. The next problem that we gave you is Rajdhani is moving at a particular speed and the next train is starting 15 minutes late. It has to maintain a particular distance. So, at what speed should that train run, or vice versa, the next train is running at a particular speed. So, what is the distance between the Rajdhani and the next express train. So, basically these are examples of structured problems. When does it become a semi-structured problem? Take the example of Rajdhani. Rajdhani has left the station. Another normal express train is running 15 minutes after that Rajdhani, and just after 15 minutes a Duronto express is travelling, which has the same speed as Rajdhani. Now, what is happening here? Now, the second train, that is the train at the middle, the normal express train, that particular train is keeping on stopping at signals. These are unscheduled stops. So, what is happening? The gap between the normal express train and the Duronto express, which is just behind, the gap is slowly lessening. So, what will happen? Duronto has to slow down again, and that will lead to Duronto express getting late. So, how do you solve this problem? Now, this is a semi-structured problem. And what is an unstructured problem? Unstructured problem, as we mentioned, unstructured problem is new. We have to find out, we can take help of different mathematical tools and techniques, but we have to find out some sort of a unique solution to the unstructured problems. Okay. Now, so that was unstructured, semi-structured and structured problems. We gave you the brief differentiation. Next, we came up to what do you mean by a model? Model is the mathematical representation or of a prototype of what is happening in the reality. Okay. It is a prototype of what is happening in the reality. We have model aircrafts. Okay. Now, this model is a mathematical representation for our usage. It is a mathematical representation. That means, if you are working with a big real life problem, if you can first make it into a model and solve the model first, see how the model is behaving, that will give you indications whether you are missing out anything, whether you are keeping anything which is not relevant. So, you see and test with the model. and once you are convinced, then you go into the real world and apply that. Okay. So, model is basically a mathematical representation of a representative set of what is happening in the reality. So, this part we have covered. Then we came to solution techniques. Now, in solution techniques in modeling, we have optimization, heuristics and simulation. In optimization techniques, what we do is we try to optimize given the limited resources or the constraints that we have. And here we have three types: linear programming, integer programming and non-linear programming. Now, linear programming we have covered in the previous lecture. Today we will do integer programming. Non-linear programming we will not cover in this module, because we will do enough applications of non-linear programming as we proceed with the other modules. Similarly, if you see, we will not do simulation also here. We will do it in a separate module and we will deal with one full module for simulation only. Okay. So, today we will take up integer programming as an optimization technique. Okay. Now, what is basically an integer programming? Now, what is an integer? Integer is a whole number, positive, negative or 0, right. Integer is a whole number, right. Now, you see, the linear programming problems that we solved, the solution had come in some places in decimals. Okay. Solution has come in decimals. Production, we came up with 540.28, but that is not possible. We cannot manufacture 540.28 units. So, ideally it is integers, okay. It is a whole number. Okay. So, integer programming deals with when situations will be like we have to have whole numbers in the model. Okay. So, that is what is integer programming. Okay. So, let us proceed with integer programming today, right. Integer programming. In integer programming, some or all of the variables must be an integer, that is a whole number or 0. Okay. In integer programming, some or all the variables must be an integer, that is a whole number or 0. Thus, some variables can have fractions, but some variables will have to have a condition that it is a whole number. Okay. Some can have 0 and yet some can have 0, 1 values only, that is either 0 or 1 values. Okay. Right. For example, now what do you mean? This looks to be a jargon for the time being, that what is this, what is that. Okay. Say you are planning a vacation, right. You are planning a vacation to some place. Now, you are planning a vacation to some place and you have choices, you have 3 choices. You are planning a vacation to place 1, place 2 and place 3. Now, definitely you can go to only one place, because your holiday is limited. You can choose only one place. So, if you choose place 1, place 2 and place 3 automatically gets cancelled out. Okay. So, it is a 0, 1 problem, that is either place 1 is selected or it is not selected. Go to the last, look at the last bullet point, and yet some can have a 0, 1 value. Okay. Some can have 0, 1 values only, that is either 0 or 1. So, if you choose to this destination 1, so either you choose it or you do not choose it. If you do not choose it, it is a 0. If you choose it, it is a 1. So, this is called as a 0, 1 problem. Okay. And also, if you see, if you choose to this, say if you can choose only 1, if you choose only to this destination 1, then to this destination 2 becomes 0, to this destination 3 becomes 0, because you can go to only one place, you have already selected your destination. Okay. It is like studying. You have chosen you had the option based on the marks that you have obtained in your examination, you had the option to take admission into 3 institutions. Now, if you take admission into institution 1, institution 2 and 3 you cannot take admission. So, either you take admission, that is 1, or you do not take admission, that is 0. Okay. In some cases it will be like 0, 1 for all, means if you take admission in 1, all the others become 0, because you cannot take admission there. So, this is called as a 0, 1 problem. Okay. So, this is a 0 1 problem. Now, some linear programming problem, now look at this very carefully. I am reading it out because it is self explanatory. Some linear programming problems are actually integer problems. For example, if we are solving how many S and D type bags we will produce, this was example 1 of module 2 third lecture. Okay, that is just today we are in the 5th lecture of this module, so 3rd lecture of this module. So, we remember standard bags and deluxe bags that we were manufacturing. So, if we were solving how many standard S and deluxe D type bags we will produce, the solution came in as 254.28 S bags, but we cannot have a fraction. So, rounding off was necessary. We could manufacture 254 bags and then we did sensitivity analysis. Okay. That is within what range can we continue. So, rounding off was necessary. Wherever, I am just reading out, okay, because this is simple but important. Wherever simple rounding off helps, we should try to avoid the use of integer programming. I am sorry, there should be a correction here. We should try to have, just a second, we should try to avoid the use of integer programming as it is harder to solve. Wherever simple rounding off helps, we should try to avoid the use of integer programming as it is harder to solve. We understand that this linear programming problem is actually an integer problem, because it has to be a whole number. We cannot manufacture fraction of a bag, it has to be a whole number, but we use simple linear programming because we know that we can round it off. It is not, it will not make that much of a difference. Okay. But if it was a warehouse, if it was a multiplex and we were having 254.29, that fraction, if we round it off to 255, that means lot of extra cost. If it is a overbridge, railway overbridge, rounding one more extra bridge means lot of cost. So, in some cases you need to have integer programming, but in some cases you can do with simple linear programming. That is what these two slides mean. Okay. I am repeating, wherever simple rounding off helps, we should try to avoid the use of integer programming as it is harder to solve. Okay. So, what do you mean by integer programming? Let us take an example. Max 2x1 plus 3x2 subject to, this is just an arbitrary one. So, do not try to solve this, we do not know whether it is solvable. Okay. So, it is just an arbitrary equation that I wrote down. Max 2x1 plus 3x2 subject to x1 plus x2 less than equal to 2, 2/3 x1 plus 4x2 less than equal to 3, where x1 x2 is integer, means whatever solution we get, we will get the solution as a whole number. Okay. You will get the solution as a whole number. Okay. If we remove the last constraint, that is x1 x2 is integer, this becomes a simple linear programming problem. Okay. This becomes a simple linear programming problem. Now, here I have something to say. Okay. That is, this one, just give me a second. Okay. This one, this 2/3 x1, you will say that, but we have a fraction here, this is not an integer. No, this may not be integer, this can be a fraction, because I am requiring 2/3 of a resource, that I cannot make a whole number. I have a 1 kg of rice, to manufacture muri or some other chudwa or something, I require 2/3 kg of rice. So, I cannot make it a whole number. What this says is, the solution that you get for x1 and x2 these two will be whole number, these two will be whole number. That is what it says. The solution that this x 1 x 2 integer means the solution that we generate, that should be whole number. Problem formulation can come in fraction, but solution will be in whole number. That is what we mean by x 1 x 2 is integer. Okay. Okay. So, this is what we want to say. Yeah. Now, next we come to 0-1 integer programming problems. We just gave you an example of 0-1 integer programming problems, that is, I have a vacation, either I go to some place or I do not go, right. So, if I go, it is 1, if I do not go, it is 0, right. So, these are called as a 0-1 problem. Okay. I may not go, I can go, these are called as a 0-1 problem, right. Okay. I want to buy an apartment. Do I have the I want to buy an apartment beside a river. Sorry, let me just erase this. Yeah. I want to buy an apartment beside the river. Okay. Yeah, in Mumbai. Okay. But I do not know, this is my dream, but my workplace is somewhere else. So, either I buy, or I do not buy, right. Either I do not or I buy. Either I can get it or I do not get it. So, if I do not get it, it is 0. If I buy, it is 1. If I do not get it, it is 0. If I get it, it is 1. Okay. So, these are some examples of a 0-1 integer programming problem. Okay. Just give me a second, let me erase. Yeah. So, these are examples of a 0-1 problem. Now, if you see, again we are mentioning 0-1 integer programming problem, structured problem, whether to open a center in a particular area. I have some land, do I use that land to open a shopping mall? Okay. Semi structured problem will be, you already have, that is a 0-1 problem, do I open a shopping mall or do I not open a shopping mall? Semi structured problem, you already have a facility, I do not want to shut it off. So, what do I do now? I do not want to shut it off. Look at the second problem, you already have a facility, I do not want to shut it off. So, what do I do? Okay. So, these are all examples of 0-1 problems. Okay. Okay. Now, one example, let us take an integer programming example, this will help us. Okay. A company, now listen very carefully, we will be able to do this integer programming problem. A company has the following warehouses A, B and C. Okay. Markets are D, E, F and G. So, the warehouses may be Delhi, Mumbai, Kolkata, the markets are Delhi, Mumbai, Kolkata, Madras and maybe Pune and Bangalore. Okay. So, the company has the following warehouses A, B, C, markets are D, E, F, G, H. Now, there is a market to sell for the product and there is a demand in the market. What are the demands? 200, 300, 400, 500, 600. Okay. These are the demands 2, 3, 4, 5, 6. Okay. 2, 3, 4, 5, 6. Okay. The demands are 200, 300, 400, 500, 600. 200 for D, 300 for E, 400 for F, 500 for G, and 600 for H. Okay. Right. So, demand of the markets are these. Market demand is this, but how much can the warehouse hold? Warehouse has to keep the product, then only they will go to the market. So, warehouse capacities are 1000, 1500, 1000, 1500, 1200. So, A is for 1000, B is for 1500 and C is for 1200. Okay. Fixed cost of the warehouses are 5000, 10,000 and 15,000 respectively. Okay. Because warehouse is a fixed cost, it has a rent, it has so many other units, and the cost table is given in the next slide. Okay. Yeah. What do we mean by that? Whatever we have said is given here. What did we say? The demand for the cities are given here. D was 200, E, D is the demand for the city. Okay. Okay. Demand for the city markets were D, E, F, G, H. Warehouses were these A, B and C, and each warehouse had a capacity of 1000, 1500 and 1200. Remember, these were already given to me, and the cost of these warehouses were 5000, 1000, 10,000. Sorry, cost of these warehouses, warehouse A was 5000, 10,000 and 15,000. These are the fixed costs. So, this may be the warehouse rent. Okay. This may be the warehouse rent. So, these were the parameters which were already given in the previous slide. Okay. Now, what are these 2, 3, 4, 2, 3, 4, 5, 3, 2, 7, 5, 1, 3. These are the transportation cost for moving one unit of product from warehouse A to market D. Transportation cost of moving one unit of product from warehouse A to market E, from warehouse A to market F. Okay. These are the transportation costs for moving one unit of the product. Okay. Question is, so what is the question? The question is, which of these warehouses I should keep? So, question is, which warehouse I should keep, and how much to transport from which warehouse? Which warehouse I should keep and how much to transport from which warehouse? Okay, right? What is the core issue in this? Okay, so what I will do is I will erase them. What is the core issue in this problem? What do we want to get here? Sorry. Yeah. What do you want to get here? What is our objective as a business owner? As a business owner, my objective is what? Minimize. What to minimize? Minimize total cost. Total cost is equal to fixed cost of these warehouses, plus variable cost of transportation. Okay. These costs will change according to output moved. This is the cost of transportation per unit of output, right. Okay. So, these costs will change, agreed. So, this is my model, minimize total cost, that is fixed cost plus variable cost, agreed. What are the constraints? Constraints are A can hold 10,000 units at the most, B can hold, B means warehouse B can have 1500 units at the most, and warehouse C can have 1200 units at the most. D has a demand, this is one, that is the supply constraint. What is the demand constraint? D has a demand of 200, so even if you send them 400, they will not be able to sell. E has a demand of 300, even if you send them 600, they will not be able to sell. F has a demand of 400, G has 500, H has 600. Okay. So, my objective is to minimize cost, and these are my supply constraint, constraint 1, constraint 2, constraint 3. These are my demand constraints 4, 5, 6, 7, 8. What are the other constraints? The other constraints are warehouse A, this is the cost, this is the capacity, this is the cost. Now, look at it very carefully. What is the total demand? Total demand in the market 200 plus 300 plus 400 plus 500 plus 600 is equal to 2000. If I open any two warehouses AB, BC, AC, any two combination of warehouses, my demand is met. These two, any two warehouses can store my total demand. So, I need not have all three warehouses. Any two warehouse can store the total demand. So, I need not have all three warehouses. So, every warehouse has a chance or an opportunity or situation to remain open or to shut down, right. Every warehouse has a chance or situation to remain open or to shut down. So, warehouse A has the option to remain open or to be closed. Warehouse B has the option to remain open or to remain closed, and warehouse C can remain open, can remain closed, right. This is called as a 0-1 problem. Okay? Clear? Okay. So, let us go to the next slide. So, if you model it, this is my model. I know it is difficult to see on the screen, font size is less. So, what I have done is this model I have broken into 2-3 lines and I am showing in the next slides. This is my objective function. I do not know how much products will move from which warehouse to which market. Okay. So, I do not know how many products will move from A to D. Quantity I do not know, cost I know 2 rupees per unit, cost is 2 rupees per unit, but quantity I do not know. So, x1 quantity moves from warehouse A to market D, x2 moves, x3, x4, and it continues. So, what is my total cost? Variable cost, this is my fixed cost, this portion is my fixed cost. My variable cost is 2x1 plus 3x2 plus 4x3 plus 5x4 plus 3x5 plus 3x6 plus 1x7. In this way, it continues up to x15. Okay. So, if you see now, this continues up to x 15, okay, variable cost, plus let us go back, 5,000 is the fixed cost. When? Only if warehouse A is open. We need two warehouses, I just showed you, because my total demand was 2000 units, total demand was 2000 units, and my supply, if I look at it, two warehouses are enough to meet the storage requirement. Okay. So, 5,000 is the cost of this warehouse provided it is open, right. So, what we will do, just like we did 2 x 1 here, what we will do, 5,000 y 1, okay. So, it will be 5,000 y 1 and where y 1 can be only 0 or 1, right, agreed, where y 1 can be only 0 or 1, that is, it is either open or it is closed. Okay. So, this is basically what we have mentioned here, 5,000 y 1, y 2, y 3. Okay. And just go here at the end, if you go to it, y 1 can be greater than 0, y 1 can be 0 greater than equal to 0, less than equal to 1, and it is an integer, that means it has to be a whole number. So, y 1 can basically only be 0 and 1, y 2 can only be 0 and 1, y 3 can only be 0 and 1, agreed. What are the other constraints? My supply, let us go back, x 1 plus x 2, x 1 plus x 2 plus x 3 plus x 4 plus x 5, this total quantity is less than equal to 1000 capacity. I cannot store more than my capacity, right. X 1 quantity I have to move to market D, x 2 to E, x 3 to F, x 4 to G, x 5 to H. So, I cannot, this total cannot be more than 1000, right. So, x 1, x 2, x 3, x 4, x 5 is less than equal to 1000, 1000 y 1. Why? Because y 1 is what, 0 or 1, means I can only supply provided it is 1, that is provided it is open, right, that is y 1. Okay. I can only supply provided it is open, right. So, in this way my supply constraints and these are my demand constraints, right. Okay. So, just look at this number, x 1, x 6, x 11. So, x 1 plus x 6 plus x 11 is equal to 200, this is the market demand. Okay. Now, this, so we broke up this problem just for easy viewing. So, but if you look at it, this is the entire problem. Okay. Your objective function, the supply constraint, the demand constraint and the integer constraint. So, if you solve it, if we use LIPS, we find that the minimum cost is 21,100. Okay. The LIPS model is anyway given. So, if you want, you can download the software and copy paste this model and see how it is behaving. Okay. What results are coming, you will see that this result is shown exactly in this manner. Okay. And this is the movement x 1. What was x 1? X 1 was warehouse A to market D, we should move 100 units. What was x 3? Warehouse A to market F, right, D, E, F, G, H, right, we should move 400 units. X 4, D, E, F, G, right, 500 units. Okay. And ultimately, we see that y 1 is open and y 2 is open, y 3 value is 0, that means it is closed. Okay. So, this is how we do integer programming. This is one application of integer programming. that we will need when we do the materials management part of this module. I just wanted to show it to you here to tell you how this integer programming works. Okay. These are the references. So, thank you.